Okay, so we're going to figure out the pH of a weak acid solution, which in essence means that we want to figure out the the H plus concentration first, and this is our acid that we're working with. And I just want you to take a good glance at that because that's cruel to have to write that over and over again. And to be candid, I'm not going to. So one of the things that we can do, and it's totally legitimate, is we can abbreviate all of this with whatever expression we want. Because in reality, the only thing that matters is that this is H plus some tail end stuff, right? So they give us trimethylacetic acid. That's a mouthful. So I'm just going to call this H tri. Yeah? So then let's write our equilibrium expression for H tri. And it's going to look like this. H tri plus water. And again, it may feel weird doing this. We're going to write this as aqueous. But we really only care about this H plus. This right here, we're not doing anything with it. So instead of writing this whole thing over and over again, we can just write it like this. And when we do that, we're going to throw it into water, which is a liquid. And at equilibrium, it's going to form H3O plus. That's supposed to be a 3O plus. Plus, didn't we lose this hydrogen off of this? And that's a plus sign. So wouldn't that give us a tri minus? And again, if you're looking at going, wait, how in the world am I writing this? Totally legit, totally okay to do because it doesn't matter. Now, it might help you somewhere in here to write that tri is equal to this right here. But either way, this is our overall equation. Additionally, whenever we do problems like this, I like to right from the get-go write what the equilibrium expression is, just so I have that in my back pocket. So I'm going to write this as Ka is equal to H3O plus concentration times tri minus concentration all over H tri. Again, why do I not include this H3O plus down here? Because it's a liquid and they don't go in here. So then let's set up our ice problem. And they give us in this problem the initial concentration of the trimethyl acetate acid, or H tri as we like to call it. So we're going to do ICE. And initially we have 3.7 molar of this, and we have none of this, and we have none of this, and as always, we don't care about our liquid. Now, again, they were very gentle with us, and this is why we can do this. It's a 1:1:1 ratio. If you take a look, the coefficients in front of each of these is a 1. What does that mean? If I lose something from here, I'm going to gain the same amount here and here. Now, since I only start off with 3.7 and I have nothing on the product side, the only direction our reaction can go is that way. So what does that mean? That means we're going to lose, boy, that's a plus sign, isn't it? I'm going to get rid of that. We're going to lose X, and on this side, we're going to gain X, and we're going to gain X. And at equilibrium, we're going to have 3.7 minus X, and here we're going to have X, and we're going to have X. And all of that we can put into our equilibrium expression. Again, through the magic of I have an iPad, I can take this right here and drag it down and make it look even more ugly. I can drag it down to right here, and then all I have to do is plug in the values they've given me into this equation, right? So when I do that, and by the way, we can't solve this unless they've actually given us a Ka, which they have. And also a gentle reminder, there's two types of problems. Either they give you the Ka and they ask you to solve for concentrations and then pH, or they give you concentrations and ask you to solve for the Ka. This is the second part of that. So let's plug our values in. And if you see here, we're going to have X times X all over, boy, I don't know why I wrote H in there. That shouldn't be there. Let's scribble that out. Over 3.7 minus X. And that's all going to be equal to 9.33 times 10 to the negative 6. Now, this is a really, really small K value, which means that we can do a 5% rule right here, or like we like to call it, the dead frog. Look at it for a second if you can't figure that one out. And if we rearrange this equation, what we're going to end up with is X squared is equal to 9.33 times 10 to the negative 6, all divided by 3.7. So if we want to take the square root of that, square root of both sides, right? What we're going to end up with is x is equal to 0.005875. Now, that is also equal to, and this is what's important, if you just write this right here and you're like, all right, that's my answer, that's not good enough because they're not asking you to solve for x. They're asking you to solve for the pH, right? So in order to figure out the pH, we have to first figure out the H plus and then figure out our pH. So we have to somehow draw the correlation that at equilibrium, the X is equal to H3O plus. I mean, the X is also equal to tri minus, but we don't care about tri minus because they're not asking us to solve for P tri. They're asking us to solve for pH. So somewhere in our equation right here, we need to associate this with H plus or H3O plus. It doesn't matter which one, they are the same value. And then if we take the negative log of that, negative log of our H plus, which is 0.005875, we're going to end up with 2.2310. Now, how many significant figures are we allowed to have in our answer? This is a really kind of a big deal. Let's look back at our original problem. They gave us 2 in our problem, right? So that means that when we come back down here to our pH, we can only have 2 numbers in our answer as well. So I'm going to write pH is equal to 2.2, and I'm taking a quick look here, 2.2. And they tell us, I would have written 2.2, but they tell us to round to 1 decimal place, which is kind of brutal. But the correct significant figures would have been 2.23, but they want us to round to 1 decimal place, so that would be 2.2 only for this problem. Now, by the way, and this is one of the things that we check often, in order to figure out if this is really less than 5% of 3.7, we could actually take this 0.005857 and divide it by 3.7. And when we do that, we can multiply by 100, and we're going to see that that is way less than 5%. So our approximation was actually pretty good. Hopefully this has helped.